أكثر حاجة ولا بلاش معك؟ هل معك الدكتور؟
All right. Assalamu alaikum. Can you hear me, guys? Do you hear me? Perfect. Now, inshallah, we will continue the second half of the chapter, which is about chapter 9, the reactions of alkynes. Now, we will start this lecture with the hydration of alkyne. All right, hydration of alkynes. Hydration of alkynes should follow the same hydration of alkene, but instead just there is some slight differences. For example, if we take this example, CH3 C triple bond CH, and then we allow it to react with mercuric acetate, for example, or adding H2O in presence of mercury, it's fine. Addition of H2O in presence of mercury and sulfuric acid, and mercuric sulfate, mercuric sulfate. It's like a catalyst actually. As you can see, this is hydration reaction in presence of acidic media. What's going to happen based on the hydration reaction of alkenes, this reaction must follow Markovnikov rule. So in this case, the positive part of the H2O should add itself to the carbon with more number of hydrogens. You can see this carbon connected to a hydrogen, this carbon connected to 0 hydrogens. So therefore, what we are going to get as intermediate product, we are going to get this type of product, C double bond COH and then double bond CH2. This is an intermediate, we call it enol, and this intermediate is not stable. It will directly change or reacting or converting into another product, which will be CH3 C double bond O CH3. So we'll get a ketone at the end of the day. This is called keto form. This is keto, this is enol form. As you can see. Now, generally speaking, keto form is more stable compared to the enol form. Anyone has any explanation why should this be? Why keto form in general it's more stable compared to enol form? Enol, what's the meaning of enol? Actually, it's the enol. It's like we have two functional groups: the ene, which represent the alkene, and the ol, which represents the alcohol. As if we have an alcohol attached to a carbon double bond carbon. In this case, whenever we have such type of functional group, we call it enol. It's a combination of both. So generally speaking, this enol form will directly convert in a very fast, rapid equilibrium. It will be converted into the keto form, and this type of equilibrium we call it tautomerism. Tautomerism. It's an equilibrium, like in its special type of equilibrium, which we call it tautomerism. Anyone knows or may guess what's the reason for such type of tautomerism or such type of converting from alcohol to, yes, I will now. Such type converting enol to keto form. Anyone knows? Anyone may suggest what's the reason for this or behind it? I did, Fatma. I did record the lecture now. I'm just waiting some answers. Anyone knows or may guess what's the reason behind it?
Because of the substitution.
So what? What's the difference between enol form and the keto form?
There is the double bond for oxygen.
Mm-hmm.
This is more than OH.
No, here you can say here we have double bond carbon double bond O carbon double bond O. Here we have carbon double bond carbon. So this is your comparison supposed to be. Which one is more stable or which one is stronger bond? Yani, because simply the stability depends on the strength of the bond. Which bond is supposed to be stronger? Carbon double bond O or carbon double bond carbon, and why? Which one?
For oxygen.
Carbon double bond O is stronger compared to carbon double bond carbon. Why?
For atomic number, because of atomic number.
So what? Yani how the atomic number will affect the stability of the carbon double bond carbon?
I know that because of the substitution. Is it?
No. Aisha, electronegativity higher. What's the electronegativity higher you mean? What exactly you mean? Elaborate more, please. Maybe if you open up your mic would be better. Hajar, polar. What's the meaning of polar? What's the polar? Don't say half answer. Just simply express yourself in a very comprehensive, detailed answer. Why carbon double bond O supposed to be stronger compared to carbon double bond carbon?
Maybe because of the carbocation.
What's the carbocation here? There is no carbocation here. It's just we are comparing two bonds. Carbon double bond O, carbon double bond carbon. Which one is stronger and why? Logically.
Because it looks like it's connected to oxygen.
No. Don't mix up things. No. It has nothing to do. That's a priority which is just related to nomenclature, like IUPAC nomenclature. If the E and Z or R and S and so on, that's totally different story. We're talking about reality. You have carbon double bond O, you have carbon double bond carbon. Which of the two bonds is stronger and why? We said it looks like very obvious that the carbon double bond O is stronger bond compared to carbon double bond carbon. The question is why? All right, I don't want to spend a lot of time on it. Now, as you should all know, that there is a significant difference in the electronegativity between the carbon and the oxygen. Based on the difference in the electronegativity, the carbons should carry a partial negative, while the oxygen partial negative, while the carbon partial positive. While carbon almost the same electronegativity. So this polarization, due to the polarization of the bond of carbon double bond O compared to carbon double bond carbon, the carbonyl stronger bond compared carbonyl is stronger bond compared to carbon double bond carbon. Therefore, this is more stable. Do you follow me? That's actually the reason behind it. That's the reason why we couldn't get this intermediate. We couldn't isolate this intermediate. The only product we got or we could isolate is simply the ketone here, because here as we said, keto form is more stable than the enol, and this is here what we call a tautomerism. So what's the tautomerism? The tautomerism in general in the organic chemistry, it's what we call it rapid equilibrium. Rapid means fast, very efficient equilibrium, but yet it includes a movement of a small atom, and most likely a hydrogen here, which includes movement of small atom, most likely hydrogen. Here you can see what's happened exactly. What's the difference between this and this? Here, just let me redraw the structure just to make it more clear. Carbon, CH3, COH, double bond C, and then CH2, right? What you can see here, what's happened exactly, this here will transform in a rapid equilibrium into CH3, C double bond O, CH3. What happened exactly is this hydrogen, which I'm going to specify by the red color, as you can see, has been moved from the connection to the oxygen to the connection of the carbon, and simply this double bond has been simply changed. But you can imagine it as this. Most likely the bonding pairs will be going here, and this goes there, and then the hydrogen will be transferred to there. Anyway, at the end of the day, what's happened in the tautomerism, and that's always the case, any tautomerism is a rapid equilibrium which includes movement of small atom. Here, this hydrogen has been moved from this oxygen to this carbon to get the ketone. To make the story short, whenever we hydrate alkyne, the end product, what we are going to get is ketone. We are not going to stop at this level because, as I said and as I explained, this enol form is not stable. We are going to get the stable product, which is in this case the ketone. Is that clear, guys? Is there any questions so far?
Victor,
Yes, please.
the first one and the second one, can we consider them as the same compound?
The first one and the second one?
Yes.
No, they are isomers, and they are structural isomers, you can say. This compound and this compound, totally different compounds. They are not the same. Because in order to be the same, دائما always, in order to be the same, the two compounds must have the same molecular formula, the same geometrical formula, in other words, the same connection of the atoms, and as well the same even dimension of the atoms in the space. Here, it's very obvious that the hydrogens are connected, the atoms here in this compared to the two compounds, atoms are connected differently. Then definitely they are different compounds. Got it? That must be right away. You should recognize that these two compounds are totally different compounds. Because if from the beginning, if they have the same molecular formula, but they have differ in the connectivity of atoms, then right away they are isomers, they are structural or geometrical isomers. Got the point?
Yes.
All right. Now what's happened here now? The mechanism of the reaction actually, how it works, and why it gives actually, and what's the reason why we are adding the mercury atoms in this case. Here, first step actually, the electrophilic part in this case here, first, the mercury, the Hg plus 2, will add itself to the carbon with more number of hydrogens, which is in this case, this carbon. And so that bonding electrons will go here, and the first step here, as you can see it in your slide, CH3, C1, CH, and then attached to Hg plus. Do you follow me? طبعا of course Hg plus then SO4 minus 2 now in this case here when this goes here I'm sorry there is a carbon, so there is a carbon and then CH3. You can see here this carbon definitely should carry a plus now. In the presence of water, the water will add itself, of course the lone pairs of the water, they will add themselves to the carbon, and then it will lead to then what you are going to get CH3COH2 plus, then CH double bond Hg plus SO4 minus 2, and then here losing H plus will give CH3COH double bond CH attached to Hg, and then finally whatever, and then finally addition of H plus, the H plus here will replace the Hg, and then we are going to get finally the enol form OH double bond CH2. This is the enol, and then finally, as we said, the enol, it will tautomerize, it will be converted right away into CH3 C-O-CH3. That's actually the mechanism of this reaction. As you can see, first electrophilic part adds itself to the carbon with more number of hydrogens, and then will produce a carbocation at the carbon with less number of hydrogens. Then the nucleophile adds itself to the carbon, and then this here, which is where we have the Hg. The Hg now will be hydrolyzed by H plus, and then we get it at CH2, and then finally the enol form will be converted into the keto form. Now, to make the story short, whenever I ask you to write down what's the product, if I'm not asking you about the mechanism of the reaction, if I'm not asking you about the mechanism, if I'm only asking you about the outcome of the reaction, so what's the major product here? You should recognize that intermediately, you don't need to write or to draw the structure of the enol. All what you have to write simply is the structure of the ketone. Do you follow me? Now, that's generally speaking the outcome of any hydration reaction of alkyne. Do you follow? Now, we have to mention that here this alkyne is unsymmetrical, but in case you got CH3, C triple bond C, CH2, CH3, and we allow this to react with the same reagent, H2O, in presence of mercury sulfate and presence of H2SO4. So what would be the outcome of the reaction? As you can see here, the two carbons making the triple bonds, they are unsymmetrical, but they have the same number of hydrogens, which is 0. In this case, what should be the product? And where is the carbonyl here? Will the hydrogen add here and the carbonyl there, or vice versa? In this case, we are not going to get any selectivity. We are going to get two products where we have the carbonyl at the first carbon plus the other carbonyl C-O-CH2, C-O-CH2, CH3. So we are going, in this case, to get a mixture of products. So to make the story short, we are only going to get one keto compound if we have unsymmetrical alkyne. If we have symmetrical alkynes, which means this is simply the two carbons attached to the same number of carbons. In this case, we are going to get two compounds. So, generally speaking, we name this, or we classify this as terminal alkyne. When the triple bond coming, or simply the position of the triple bond at the end of the chain, we call it terminal alkyne. If the triple bond is inside, it's just, we call it just normal alkyne. It's just alkyne. So just to differentiate any alkyne from the terminal, always the terminal, because simply the terminal is the meaning of the terminal. It's like the side, the طرفي, الجنب. So when this carbonyl, or when this triple bond, the position of it, it's at the end of the chain, then we call it terminal. In here, we call it just normal alkyne. Any questions so far, guys? Is there any question so far? All right. Now, the other question, which is the other reaction, which is hydroboration oxidation of alkynes. Again, similarly, the next reaction, which is similar to the reaction of alkenes, which is hydroboration oxidation of alkynes. Now, if you remember, when we have, for example, C triple bond CH, for example, or let's just take specific example. Suppose here CH3. If we take unsymmetrical alkyne, if we allow it to react first with BH3 in presence of THF as a solvent. Second, if we then reacted or allowed to react with sodium borohydride by reduction, based on the Markovnikov rule, based on this reaction, the alkene, we said this reaction is anti-Markovnikov rule, in which we will get hydration. At the end, we are going to get hydration and micro. Oh God! Markovnikov rule. So we're gonna get hydration based on Markovnikov rule. Do you follow me? Now, similarly, that's actually what we are going to get. And what's the hydration? So if we ignore now the mechanism, we just focus on the product. What we're gonna get? It's hydration. So hydration means all of this is like an equivalent of addition of H2O. Like we have two parts, hydrogen and OH. Based on this, on this information, on what we have studied in the reactions of alkenes, the hydrogen, which is the electrophilic part, should add itself to the carbon with less number of hydrogens because it's anti-Markovnikov, and the OH will be there. So what we're going to get, we are going to get CH3, CH, then double bond, CH, then OH. What we call this reagent here? What's the name of this functional group?
Enol?
Yes, it is enol because simply it is alkene attached to alcohol or alcohol attached to carbon double carbon. ايش مش واضح؟ عفوا مريم. يعني الخط مش واضح ولا ايش مش واضح؟ ولا البورد مش واضح؟
لا يعني الصورة مو واضحة، أنا شايفة شريط صغير.
الآن أقرب البورد أكثر؟ ولا بجوز الكتابة أعيد يعني كتابتها مرة أخرى؟ بعيدها ما في. بعيدها إذا بدك ما في مشكلة، بس المهم هذا this functional group is enol form, right? So again, this will definitely then tautomerize, most likely to C double O now H, analdehyde as F here. So this is enol. The enol form is not stable. It will be converted into the corresponding aldehyde if we have unsymmetrical, if we done the hydroboration oxidation on unsymmetrical alkyne. Do you follow me? So again, it's the same reaction like The same mechanism even like the hydration of hydroboration and oxidation of alkene. Do you follow me? Is that clear, guys?
Yes, Doctor. Yes.
Doctor,
Yes, please.
the last thing is CH3 or just H?
The last what? Here?
Yes.
This is hydrogen. Hydrogen. Because see simply here, what's going to happen? This hydrogen will be removed, will be transferring into this carbon, and the double bond will be moved here. So it will get simply, oh, there is a carbon missing. I'm sorry. You are right. There is a carbon missing here actually. There is here supposed to be CH2, then CH3. CH2, and then CH3, CH2. This is simply the compound. Because simply we have 3 carbons here. We're supposed to get also 3 carbons in the product there. Clear, guys? All right, I will use another marker now. Anyway, let me just give you another example, just to make it more clear, because so it looks like the writing was not clear. Let me take another example. Here, for example, why these markers are so bad? Let me just check. This one is better. All right. Suppose we have symmetrical now. CH3, C, triple bond, C, then CH3. Is the writing clear now? Perfect. Now let's make a hydration reaction or hydroboration reaction via hydroboration oxidation, which in this case, what we need to add first, we need to add pH3 in the presence of THF, and then second H2O2. In this case here, what we're supposed to get here, because it's symmetrical, doesn't matter where to go. So first of all, what we are going to get first as intermediate, we are going to get CH3, C, double bond, C, and then CH3. One of the carbons will be attached to OH, and here one will be attached to a hydrogen. Again, we are going to get enol form, isn't it? Now this enol form will tautomerize to the keto form, where we will get then simply CH3, CH2, then C double bond O, then CH3. That's actually if you have symmetrical alkyne, where we have in this case the 2 carbons of the alkyne are attached to another carbons. Then definitely our product will be ketone here, not aldehyde. Only we will get aldehyde if we have a terminal alkyne in which one of the carbons is attached to a hydrogen in this case. Got it, guys? Is there any question? Is there any question?
Doctor, can you repeat please?
Repeat this? Repeat this?
Yes.
Sure. Okay. So we have alkyne. We allow the alkyne to react with hydroboration oxidation. Remember, this is called, these reagents called, we call it, or this reaction we call it hydroboration oxidation reaction. This is the reagent used for hydroboration oxidation. From our knowledge of the previous chapter, what did we say about hydroboration oxidation reaction? First of all, what's the hydroboration oxidation? What's the net result of hydroboration oxidation? It's a hydration reaction. Got it? That's how I want you to understand, guys. It's not just, memorizing words rather than to understand what's behind the words. Got it? Here, the hydroboration oxidation, it is simply, you can say it like this, it is equivalent to hydration. I think everyone knows hydration, right? Do you know hydration? Hello, guys. Hydration is addition of water. 2 parts hydrogen OH, that's it. It's a hydration, لكن it's anti-Markovnikov rule. That's the summary of the whole issue here. So this reaction will lead to a hydration in anti-Markovnikov rule. Now, as we said before, if we're talking about symmetrical system, then it doesn't matter. Markovnikov here does not fulfill. We cannot apply it because simply there is no difference in the number of hydrogens of the two carbons. So it doesn't matter where you add the OH and where you add the hydrogen here. In this case here, because it's totally symmetric, so we'll get only one enol product. This enol product will then tautomerize, as we said, because enol is not stable. So the carbon which was connected to the OH in the enol here, this carbon here, becomes carbonyl, and this carbon, the other carbon which was attached to this enol here, it becomes CH2. That's always the case here. So we will get finally this ketone. Is that clear, guys? Clear now?
Yes.
All right. So now, if I asked you how you could, or from which alkyne, what's the corresponding alkyne you can prepare this compound? Now, we just draw the write the reaction. Which alkyne can, or show how you could synthesize? What is the structure of static material which may lead to the desired product This is here. If we have, for example, if we want to prepare such a compound, CH, then CH2, then C-double-bond-OH. From where? How can we prepare this? From which functional group we may synthesize it? First of all, is the writing clear, guys? Can you see the structure clearly, or should I rewrite it?
دكتور المشكلة ترى لما أحيانا ظهرت تكون الشبكة ضعيفة فعشان كذا ما يوضح.
I'm so sorry, guys, to hear that. But in all cases, inshallah, it shouldn't be a problem, because simply, as you notice, when I upload the lecture on YouTube, I think it becomes very much clear, right? The structures and the writing and so on. But anyway, now is it clear, or what's the case here? Clear. All right. Now, as you can see here, you may think how to prepare such a compound. You may think by this way, like these two carbons, if they were alkyne, then we may do hydroboration oxidation, then we will get aldehyde, as the previous example. So what we can guess, we should guess that if we have, this is the structure the same, the benzene here, but we have C-triple-bond CH. And then we allow this to react first with BH3 instead of in presence of THF, second by reaction of H2O2, which is the oxidation of the boron. As we said before, what's going to happen, it's a hydration reaction. The OH will go here, right? Let me just write it in just showing you in green. Just here, this carbon, what we will get, which atom here will be attached to this carbon, the green one. Which atom supposed to be attached to this carbon? Oxygen, OH, the OH. The OH will be attached here, and the hydrogen will be attached there. So that means we are going to get enol first. After that, the enol right away will be converted, or will be converted into the corresponding aldehyde. In other words, when you add this, when you've done this, you are going to get first the enol according to Markovnikov anti-addition fashion. So this will be, this will be hydrogen. This will be hydrogen, then C H OH. Then this right away will be converted without doing anything. Do you follow me? Because this is enol and that's ketone. That's keto form. It's aldehyde, but what we call it keto form, which is related to a carbonyl instead of carbon double bond to carbon. Do you follow me, guys? Because from now on you should learn. What do you mean by your question, Malik? يعني what do you mean by your question? ما ينفع العكس يعني. I didn't get it about your question. What do you mean? And please, if you can, please open up your mic.
دكتور يعني ما ينفع يصير ان الاتش ترتبط بالكربون الاولى والاو اتش ترتبط
لا ما ينفع. طيب ما ينفع لانه بكل بساطه يعني بالمناسبه يعني this reaction, the generator or the inventor of this reaction, his name is a scientist very famous in the organic chemistry. His name is Herbert C. Brown. He is a Nobel Prize laureate. What does that mean? He is awarded the highest award in science, what we call it Nobel Prize. I think you all guys heard about it, right? Did you hear about Nobel Prize?
Yes.
Now there is a scientist, his name is H.C. Brown. I hope you just for curiosity, just Google this name and see what he has done and why he has been awarded this top science award, which called Nobel Prize. Why the scientific community, they award him this award? Because of this reaction, because of hydroboration oxidation reaction. Hydroboration oxidation reaction, it enables us as organic chemists to make hydration in anti-Markovnikov fashion. Do you follow me? Because all other hydration procedures were leading always to Markovnikov fashion. Do you follow me? Yeah. In other words, hydration, it either can be Markovnikov or anti-Markovnikov, right? So for example here, C double bond C, suppose C triple bond or C double bond C. For example here, H, and then R. When you do hydration, you have two ways of doing hydration. Let me just take this away. When you make hydration, it's two ways of doing hydration. Either the conventional ways of doing it, which is simply by, for example, the best procedure, as we said, is mercuric acetate first, followed by, I think, I forgot actually what's the reagent supposed to be. Anyway, for example, forget that now for the time being. For example, H2O in presence of H+, this is Markovnikov fashion. While if we use hydroboration oxidation, which is BH3 in presence of THF first, second with H2O, then what we are going to get anti-Markovnikov rule. Do you follow me? So you can see here, this procedure, this is the only procedure which leads to anti-Markovnikov. That's why H.C. Brown, he is the one who invented this method. He has been awarded the Nobel Prize for this achievement. Do you follow me? Now back to your question, Taif. It will never be opposite way, because simply this reaction, hydroboration oxidation, is accompanied, is connected to anti-Markovnikov rule. You always must remember that. Got it, Taif? Taif, got it?
ايوه دكتور.
تمام يا جماعة? Okay, any other question? حياكم الله. Any other question? Is there any other question? All right.
Doctor,
Yes, please.
يعني على حسب المواد اللي في السهم بنحدد إذا انتاي أو طبيعي.
طبعا that's why actually we were always يعني in the previous chapter if you remember, because it's very important. That's the core of the whole chapters, يعني chapter 7, 8, 9, all about the Markovnikov. Markovnikov always, whenever you want to answer your question, you must ask yourself, is it Markovnikov or anti-Markovnikov? Because that's actually for every reaction there is, you know, a decision if it is Markovnikov or anti-Markovnikov rule. Do you follow me?
Yes.
Sure. Now, anyway, now the hydrogenation of alkyne, it's very simple, straightforward, but the only difference between hydrogenation of alkyne and hydrogenation of alkene is just the number of moles of hydrogens needed to achieve hydrogenation. Do you follow me? Hydrogenation of alkynes. Now, hydrogenation depends on the number of hydrogens we are using actually. For example, if we have R, C, triple bond, C, R, generally speaking, we need 2 moles of hydrogens in presence of catalysts such as, for example, platinum oxide, in order to get RCH2, CH2R. Can you see it? So the only difference between hydrogenation of alkynes and hydrogenation of alkene is that in the hydrogenation of alkenes, we need actually 1 mole to 1 mole of alkene. But in the alkyne, since we have 2 pi bonds, which needs to be hydrogenated, then we need definitely at least 2 moles of hydrogens for this reaction to take place. There is another reaction which is very specific and very special, which we call it Linder catalyst, or using Linder's catalyst. Now, generally speaking, if we have, for example, this alkyne, CH3, let me just take a specific example of this reaction. CH3, C triple bond C, CH3. If we allow this to react with hydrogen, excess hydrogen, in presence of palladium over carbon, for example, excess, what we are going to get, CH3, CH2. Let me just write what's the change by the red color, hoping that this may help you in recognizing the board better. CH2, CH2, then CH3. Do you follow me? So what's happened here, what's gonna happen, it's simply, we are not going to stop at the alkene level. In other words, first of all, the first mole is supposed to be addition to the 2 carbons, so we are going to get alkene. Then addition of another mole going to full alkane, which is full saturation. Right? Now, if we use another catalyst, for example, CH3, C triple bond C, CH3, and then in presence of hydrogen, using what we call it Lindler's catalyst. And the Lindler's catalyst is actually palladium over carbon. It's palladium over carbon. Sorry, this is not palladium. I'm sorry, this is here, the catalyst here, for example, platinum. And if we use now what we call it Lindler's catalyst, we are going to stop at the alkene level. So what we are going to get, CH3C, or even here, CH3C, double bond C, and then hydrogen, and then CH3, hydrogen. Sen addition. That's actually the difference, the difference between the 2 reactions. Do you follow me, guys? If we use the normal catalysts which are used for the hydrogenation of alkenes, we will always get the full alkane, the corresponding alkane. But if we allow the alkyne to react in the presence of what we call it Lindner's catalyst, then we are going to we could be able to stop at the alkene level. Of course, we should allow it to react with 1 mole. We will stop at the alkene level and we will get it in a cis fashion. Do you follow me? Is that clear?
Yes.
So that's actually the importance of the catalyst, by the way. We name the catalyst based on the name of the scientist who discovered this catalyst, because some catalysts may affect the reaction to give you specific product rather than the other product or the other possible products in principle. Do you follow me? I'm going to stop actually at this level because I don't want to make the lecture too long, and as I promised,